Okay, so we're talking set theory today. And we're going to start off with a few definitions and kind of some just code to give a bit of groundwork. So we're going to be talking about what a random experiment is, a sample space, and events. And, I'm going to be throwing around different words for sample space and events. I might say for sample space, I might say universal set. I might just refer to it as S. Events, I might call outcomes, but when we'll see that these are kind of some of these terms are fairly interchangeable. And in terms of set operations, as I said before, union, intersection, complement, we're actually going to be doing difference as well. But as you'll see, difference is fairly simple. Okay. So the first thing we're going to think about here is a random experiment. Now I'll try to get this all on one slide. So when we're thinking about random experiments, I like to put this in the frame of some kind of observable phenomenon, right? However we want to observe it. We can observe it. We flip a coin, we're observing it with our eyes. So you flip a coin, a single flip of a coin has some kind of outcome, right? And we don't know for sure what outcome that's going to be. It's either going to be heads or tails. Let's say it's a fair coin. And, we're going to assume that we don't have a third outcome of the coin landing on its edge. We don't have the coin landing at a 45-degree angle. We don't have, when we're considering this, we're not thinking, well, you flip a coin and you don't catch it. So, there's another outcome. We're just thinking of a sanitized version of the outcomes, just heads or tails in that event. Rolling a die, let's say a 6-sided die. All the potential outcomes are 1, 2, 3, 4, 5, 6. Similarly, we can think of other types of phenomena, not just these kind of easy to constrain phenomena like a dice roll or a coin flip. We can think of somebody who's doing quality control on a line of parts that are coming out, and out of some factory operation, right? And they look at each part and they turn it over and they're looking for a specific flaw or a couple specific flaws, and maybe the outcomes are part is good, part has flaw 1, part has flaw 2, part has flaw 1 and 2, right? So maybe there are 4 outcomes in the observation of a part. And, given enough time and enough observations, the person can start to discern, or the company can start to discern, a rate of flaw 1 and a rate of flaw 2, or a rate of flaw 1 and 2, right? So in these cases, in these what we're calling experiments, random experiments, we don't have a known, we don't know beforehand what the outcome is going to be. There's something stochastic in there. There's something random in there, right? And what we want to be careful of when we're first considering whether something is a random experiment or not, we want to consider, do we have a guaranteed outcome? Because if we do, well, we've got certainty, and we don't really want to think about this as an experiment anymore. If a certain outcome can't happen, then it's impossible, right? And if we're dealing with certainty or impossibility at any point, we're not really dealing with a random experiment. Arguably, we're not dealing with a random experiment. So that's kind of a constraint we put on this definition. It's a phenomenon where we have a potential set of outcomes, right? And all those outcomes are different from each other, right? So if any of those aren't possible, then we don't include them in the set of outcomes, which may seem obvious, but you definitely want to be careful about this, depending on what you're looking at, right? If you have a coin that has 2 heads and you're considering whether or not you're going to get heads or tails, well, you're not really performing a random experiment there, even though you are flipping a coin. So how are we going to think about a set? so you've started learning sets in Python, and mathematical sets and Python sets are not really that different from each other, and we'll kind of talk about that. Really, all we mean by a set is a well-defined collection of objects, right? So let's think about this. How we might write this. Often we'll denote a set with a capital S. Often you'll see this cursive as well. And we tend to use these curly braces to contain elements of a set. And we might say elements, we might say items, we might say objects, right? All of those are interchangeable in this case. So here we've got cat, we've got dog, and we've got squirrel. What we cannot have here is duplicates. We can't have cat, cat, dog, squirrel. We could have cat 1, cat 2, dog, squirrel, right? But each element is unique. Each of these is unique. So here's an interesting thing. Let's say instead of denoting this as S, let's say I call this A instead. And I've got another set B, and B is, I don't know, elephant and person. Even though these are sets, A is a set, B is a set, we could compose another set, and I'm going to call that one S, and S is composed of the sets A and B. So notice, a set can also be an object in another set. That's just something to pay attention to. The idea of a set is fairly flexible in this way. Now, I use this capital S, and when I'm using capital S here, what I'm generally describing is something called a sample space or universal set. And this is going to be all objects that are all outcomes that are possible. Okay? So, if we're thinking about S as being a sample space, and we're talking about it containing all potential outcomes, then there's also this concept of a subset, which is composed of elements that exist in the sample space, and this subset is not necessarily exhaustive of the sample space, right? So if our sample space S contains, I'll just use numbers here, 1, 3, 9, 15, and 21, we can have a subset of S, and maybe I'll call that A, and this is often what we'll do. We'll say, well, we've got a subset of S of our sample space, and let's call it A, and A is 1, 3, and 9. So you can see that S includes A, right? A does not have any elements that do not exist in S, and in that sense, A is a subset of S. All elements that are in A also exist in S. And, likewise, we could have B, where B is 3, 15, and 21. And B is also a subset of S. We can have C, and let's say C is 3, 15, and 79. Even though there are some elements shared by C with S, C is not a subset of S. C is not a subset of S because we've got an element in here that doesn't also exist in S. I might call S a superset of A, right? Or a containing set of A. And there is a bit of, there are some semantics floating around that differ from place to place. But I'm going to try to keep it constrained to sample space universal set and subset and superset when I describe these. So when I say universal set, I might use S, I might use U, and don't be surprised. I'm not going to use this, but don't be surprised if you see capital Omega out there referring to the universal set. Let's see, anything else here? Okay. All right, so let's tie this back into Python a little bit. We can use sets, the set data type, and I want to make a distinction here. There's the set as a mathematical concept, the set theory form of set, and then there's sets in Python. The set is a data type. It's defined in the Python language as a set, and it generally does operate under the same constraints that mathematical sets operate under. But there are other things that we can potentially do with sets that are kind of cool. We use them for a variety of things. There's this thing called the list set trick, and this is incredibly helpful in Python. We use it to dedupe, and all that means is we use it to remove duplicates. So this doesn't just exist in Python; it exists in a bunch of languages. So this is just a quick way to remove duplicates through the properties of a set. Okay, so let's just define a list, and I'm gonna mash keys, and I'm gonna make sure I get some duplicates in here, and I'm just gonna put a bunch of commas in here. And I am going to remove duplicates. We can see that there are definitely duplicates in here. I can see a couple 6s and 5s and everything. The way that I can do this, a set will not allow duplicates. So I'm going to cast this list to a set. And from there, I'm going to cast it back to a list. Okay? And now I can print L1, and L1 is going to have all the elements, all the unique elements that are in the list. So let's see if that works. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And I was mashing a number pad in front of me, so it's not too surprising that we just got 1 through 9. Notice, though, this output is not in the order of the occurrence of these elements in the original list. And that's because a set does not assume a specific order, okay? We think of sets as being an unordered data type, and for that reason, you can't guarantee order. And there are a lot of cases where you do want to guarantee order, right? We can use lists for that, but we can't really use sets for that because we can't predict the outcome order of the elements after we process through a set. So this is going to bring us to our first challenge. And after this challenge, we're going to jump back to random experiments a little bit because there's something I want to kind of... I'm going to continue seeding an idea. And when we get to it, hopefully a lot of the fundamentals of that idea will be fleshed out, right? So I'm going to get to that shortly. Okay, so the breakout for this, you're going to write a function called dedupe in order. That function is going to take a list, and that list can contain duplicates. It can contain duplicates. And what you want to do is return a list that has no duplicates. Don't use the list set trick to do this because you want to maintain the order of the elements in that original list, okay? So if we're thinking about this case, 6, 5, 4, 3, 2, and then you wouldn't want to include 4 because it already happened. And then you would want to include 1, but not 6. You would want to include 8, but not, and 7, and 9. And I think that would get you there. And then the rest of these are going to be duplicates. So you would want to have an output list of 6, 5, 4, 3, 2, 1, 8, 7, 9. Right? That would have duplicates removed, but you would maintain order. Okay, so let's do 4 minutes for this. And try to get to a working solution, and then we'll code through it. Okay, so I'm going to code through a solution here. We're going to call this dedupe in order, and let's pass in I'm going to just pass in a list. And we've got this other list defined up here. And so we can use that to test it when we get there. And I'm just going to make a list accumulator and call it deduped. And then for every element that's in our original list, I can simply check to see if the element is already in deduped. So if the element is not in deduped, then we can say deduped.append. We can append that element. And at the end of that, we can just return deduped. And that should work. Dedupe in order. And let's pass in the list from above, which, as we can see, has all of these duplicates. So hopefully, and I'll just print the list as well. Hopefully that'll do what we expect it to. So 6, 5, 4, 3, 2, 1, right? So we skip that 4, go to 1, we skip 6, we go to 8, 7, and then 9. So that is working how we'd expect it to work. Okay. So let's jump back over here. And let's go back up to random experiments just for a moment. And I want to code through the idea of a random experiment just to give us that basis, because we're going to come back to this kind of a lot. We're going to think of a phenomenon that is observable, something that we can write some code to model. And I'm just going to call this random experiment. And let's think of this. This is going to come back around and around. Let's think about a single coin flip. So to facilitate this, I'm going to import from random. I'm going to import choice. Give us a little real estate here. And so from random import choice, let's think of a single coin flip. So I'm going to call this coin flip. And we're just going to get one coin flip out of this. And I can return the choice, a random choice out of this list of items that are heads and tails. So that's all the choice function does. It will look at a sequence, a sequential type, like a list, and it'll return one of the items in the list with equal probability, right? These have equal weight, any of the items. Now, we could put more into this. We could model this as a die roll by doing 1, 2, 3, 4, 5, 6, right? And then there's a 1/6 probability for any given outcome. So let's think about this just as a coin flip. And let's think of the outcome of a random experiment as being the result of a single coin flip. So if we're trying to think of the... So if the experiment is the outcome of a single coin flip, then what is our set of outcomes, right? Our set of outcomes is simply heads or tails. And we already know the probability of either heads or tails. So here's a thought. What if our experiment is not a single coin flip? What if our experiment is the count of heads in 20 coin flips, right? So what if our experiment, our random experiment, is in regards to the count of heads in 20 coin flips. Well, first off, what would you expect, if you ran this a bunch of times, if you did 20 coin flips a bunch of times with a fair coin, what would be your expectation for the average count of heads in 20 coin flips? Yeah, 0.5 times 20, right, which would be 10. We would expect 10 heads, and that's that's pretty intuitive, I think. Now we can model this. We can say 20 flips, and let's just kind of pack in these coin flips. So for whatever in range 20, let's append to flips. Oops, flips dot append. Let's append a coin flip. We'll do this 20 times, right? And then we can return the flips. So let me just print 20 flips, and let's see what we get. Now, we might want to count the number of heads, because we're just seeing this big list of outcomes, and that's not particularly helpful. Well, we just got 10. Just got 10 again. 10, 9. Okay. I was about to say 13, 13, 7, 9, 12. And if we were to run this a bunch of times, our expectation, if we ran this an infinite number of times, theoretically we would get an average of 10 heads. So that's a fairly easy experiment to make. That's a fairly easy phenomenon to model, right? Coin flips are very easy to model, and we tend to use them quite a bit. Okay. So as I said, we have this idea of a sample space, and we want to consider every possible outcome. I don't tend to use the term sample point to describe a given outcome. I'll usually say this is an event or an outcome, but sample point is another word that's out there. So if we're thinking about the role of a six-sided die, here we've got 6 outcomes, 1, 2, 3, 4, 5, or 6 pips. And pip just refers to the count of dots. A pip is a dot on a die, so like, this die has 5 pips on it. This side of the die has 5 pips. So if we're thinking about the sample space for a six-sided die roll, where we're thinking about the outcomes in terms of the count of the pips, then our sample space is just 1, 2, 3, 4, 5, or 6, right? Now, we could define outcomes differently. We could define outcomes as odds and evens. We could define outcomes in terms of less than 3, less than 5, less than 6, right? There are different ways to think about the outcomes of an experiment, depending on how we talk about the experiment. And, that's just something that we're going to see throughout what we're going to do today. Really starting in our next class, we're going to see this quite a bit. Today we'll touch on it lightly. So I already mentioned this idea of a subset, and I put subsets in these terms, right, where let's think about our sample space S here as the outcomes of the roll of a die. We can define different types of events, right? So here we've got A, in which we've got the count of pips greater than 3, or B, where the number of pips is even, or C, the event in which the resulting pips is exactly 3. Now, these are all subspaces, right? These are all subspaces of S. And you might already be thinking, well, there's an easy way to determine the probability of the event A, right? So we're going to get to this later, but the number of elements in the subset or subspace, I'm going to say subset, the number of elements in the subset A divided by the number of elements in the sample space is going to give you the probability of the event A. We're going to keep coming back to that, and we're going to we're not going to do too much with that today until the final breakouts in the class, but we're going to use that as our basis for probability. So a lot of the time, we're going to represent these concepts in terms of Venn diagrams. And sorry, I just made these slides today and didn't realize that this wouldn't be quite so readable. But yeah, visually, Venn diagrams just make things kind of easier visually. So when we're talking about A, we're thinking about this in terms of some defined set of outcomes, right? And maybe this is the even values in a roll of a six-sided die. When we're talking about B, maybe we're talking about any roll that's 3 or less. And so you can see that there are outcomes that they share, and then there are outcomes that they don't share, right, on either side. And then there are outcomes that are not in either A or B. And we're going to kind of explore this through our basic set operations. So we're going to do union, intersection, set difference, and complement. And we're going to go ahead and write functions for all of these, but we're not going to use the set data type in Python. We're going to write these using lists, which may seem, well, why would we do that? But, a lot of this is really about getting the idea of a procedure across, right? So if we're going to perform union, which we'll talk about shortly, there's a way that you can use list operations to perform a set union. And, you could just take a set and do, set A dot union of set B and get the union. But we want you to look a little bit under the hood for things like this, because these kinds of operations will abstract out to so many other problems. Okay, so set union is super simple. And I'll just jump over here. I'll probably be drawing a lot of these. So here's our sample space S, and we've got A, and we've got B as events that exist in S. We talk about union as being everything that is within A and B. And this is very much like the OR operation, the Boolean OR. And basically all that means is that everything that A does not share with B, everything A does share with B, and everything that B does not share with A composes the union of A and B. Now notice we don't want to duplicate the elements that are shared, right? So keep that in mind. We will never have duplicate elements in a set. So we write this with this kind of sort of U shape, A union B. And as I said, this is very much like the OR operation in Boolean algebra, or in the Booleans that we use in Python. So with that understanding, you're going to write the union function for two lists, okay? And I'll give you a little bit of starter code on this. So this is going to be set union, and let's just call it union. So def union, and you're going to pass in two lists, list 1 and list 2, and you're going to code your solution there. So let's do 4 minutes on this, And yeah, do your best on it. We're going to be doing a number of these, and they're all going to be at about the same level of difficulty as this one. Okay, so go ahead and get started, and I will start a timer. All right, let's code through this. And I'm seeing a lot of working solutions, so that's great. I'm gonna code this, as we're gonna code, or as I'm gonna code all of these in a fairly straightforward way. And the first thing I'm gonna do is I'm just gonna make a copy of list one, and even though this is not technically true, I'm gonna call it set one, even though they are lists, we're thinking about them as being sets. So set one, I'm going to build the set union out of set one, and then I'm going to add all the I'm going to put all the elements that are in set two into set one. So the way I'm going to do this, at least, is for each item in set two, we can say if the item is not in the set union already, then we can just append it to the set union. So set union.append the item, and we can return the set union when that's done. So what's probably going to help us here is to have some values to work with. So why don't I do, I'm going to make 3 lists, list 1, list 2, and list 3. And think about different types of sciences and just throw names of sciences into the Slack really quick. So I'm going to do astronomy. I'm going to do nanoscience, do data science, do biochemistry, and see what other people were throwing in there. Sociology, and then let's start adding some down here. So let's do psychology. What else? Chemistry. Yeah. Let's throw some maths in here as well. Oh yeah, botany. Maybe some engineering in here too. Let's just do engineering. How about bioengineering and robotics? That sounds good. And do computer science. Let's do. Actually, that's probably enough. So I'm just going to grab a few of these, and I'm going to make it so that there are elements shared between these. And let's do, put computer science here. Okay. That's probably good. Why don't we do, let's also put psychology in there. Okay, perfect. All right. So what we would expect from the union of list 1 and list 2 is every element without duplicates that exists across both of these. So let's see if that's what we actually get. Let's print the union of list 1, list 2, and see what we get. Astronomy, nanoscience, and the way that I've constructed this, we're going to get all of these first, right? So we can see that that's what we are getting: nanoscience, data science, biochemistry, sociology, chemistry, and then the first one in here that doesn't also exist in list 1 is going to be our next item, so botany, and then oh, interesting. No, it's botany, then psychology, and then bioengineering, robotics, and computer science. So that looks like it's working. Now, here's the thing. The set union can be for multiple sets, right? So we just did it with 2. And, you know, we've got 3 sets there, or things that we're calling sets. They're lists, but let's think of them as if they are sets. Now, how could we build this function in order to take an arbitrary number of sets, right? Like maybe A, B, C, D, E, F, G, and H, and union all the elements across all those sets. Now, it may not be obvious how to do that offhand without packing all these things into, say, into a list that we then pass in to the function. But really what we want is to be able to define a function that can take an arbitrary number of arguments, okay? And we're going to do this using something called star arguments. So star arguments are kind of what we call, I don't know if Clark has used this term, star arguments are a form of syntactic sugar in Python. And they're really, really convenient if you don't know how many things that you intend to pass into a function. Well, you can define star arguments and then pass in as many things as you want. So let's demo this. This is pretty easy, pretty straightforward. So we're going to use this to build a better function, a better union function. So I'm going to call this star args, which really all that means is before the parameter in the function, and here we're assuming it's named args, you put a single star. And that turns this into a type of collector for all of the things that you pass into the function. So let's look at how this works syntactically. Right, so I'll just define something called star args, and the parameter will be that. So we can pass in any number of elements to this, and let's just print the type of args. Actually, I think I'm recreating exactly what we have here, aren't I? Oh yeah, I totally am. Okay. And then let's do, for each item in the args, let's print that item as well. And just notice when I'm doing this, I'm printing, I'm not returning, and I'm going to explicitly say return none because we're not returning anything. This function doesn't actually return anything. So I just want to put that in there as a reminder of the difference between return and print. So if I call star args, I can call this on any number of things. Let's call, hi, 3.1415. How about dog, cat, and then let's do, some big number, and true, none, and let's put in a list like of some numbers, 654,987. Okay. So all this function is going to do is it's going to take this arbitrary length of stuff. And you might be wondering, well, what is the type of this? Because it kind of looks like a collection when we pack it in there. We can put more stuff in there. We can put less stuff in there. It's actually going to encase it in a tuple, which kind of gives it some safety as it passes in and out of the function. That's part of why we return tuples and not lists from functions as well. But yeah, let's see what kind of output this gives us. Gives us invalid syntax on line 87. Oh, that's because I have a return in there. Okay. So notice this just, all this does is it goes through each of these elements and it prints it out each on a new line. So you might think, well, we could write a function that performs the union operation, right? And we could pass in any number of sets if we use this star args construct. So that's actually going to be the next thing we do. And let's jump over to this breakout. You're going to write a function called union of multiple sets. And this function should be able to take in, 1 to 3 to 5, however many sets. And by set, I mean list, of course. Take as many of those in and return the union of all of them. So that's going to be your starter code. And I think I have you set for, yeah, let's try 4 minutes on this, and if we need to extend a little bit, we'll do that. Okay, go to it. Do you all want a couple more minutes on this? If you do, give me a thumbs up. Otherwise, I can start coding through a solution. All right. I will code through a solution. And this will hopefully help inform the next thing that we do with star args, because we're going to use it one more time after this function. So def union multiple sets, we're passing in this star args. And again, I'm just going to make this set union. And in this case, I'm just going to start it as an empty list. And hopefully it'll make sense why instead of me making a copy. And then I'm going to say for list in the multiple sets, for each item in the list, if the item is not already in the set union, then we can say set union dot append that item. That's it, really. And I could have written this a little bit differently. I could have made the copy here, but I wrote it this way because I wanted to ensure that it would work even if we only pass in one set, okay? Because otherwise I would probably skip, in this traversal right here, I would probably skip, let me do this. Instead of calling this args, I am going to call it multiple sets. And I just want to do that because it's more meaningful. Also, it shows that you don't need to use the args keyword. It's not a keyword. You don't need to call the starred item args. We just generally do. We call them star args. So this should work, and I just need to return the set union of those. And we can print, we can just print the results of the union of list 1, list 2, and list 3. And why don't we print all 3 of those, list 1, list 2, list 3. What is this? Union multiple sets, right? Yeah. Okay. And this is just so we have a quick and easy reference for it. Okay. So here's our output down here at the bottom. And this should be everything that is in these 3 above. So why don't I just also do this. So even still, we're going to get everything out of list 1 first, right? Astronomy, nanoscience, data science, biochem, sociology, chemistry, botany. And then the next thing is psychology. We skip these next 2. We get bioengineering, robotics, computer science. And then computer science, nanoscience exists above, data science exists above, psychology exists above. So we don't end up adding anything from that list 3 because we've already got everything. But you can see that this does work for the union of multiple sets beyond 2 sets. Okay. So that's union. And the next set operation that we're going to consider is the intersection. So I'll just draw this again, and it's nice if you're trying to consider how to think about a set or a probability or anything like that. It's nice to just draw a picture really quick. So we've got our set S, our sample space S, and then we've got A, we've got B, and the intersection here is going to be represented as A with this sort of upside down U for intersection, B. And A intersect B is going to be composed of anything that they share, and nothing aside from that. So only what they share goes into the intersection. So if we're thinking A is dog, cat, rat, and B is rat, eel, squid, then the intersection is only rat, right? So the intersect of this, A intersect B, is going to be the set composed of this one element, rat. Okay. So, you may, we're going to really draw this relationship in our next lecture, but intersection is very much like the logical operator and we'll see that. Okay, so you're going to code the intersection function for two lists, and after that we're going to, you know what? Let's take a break before we do this. Let's take 5 minutes, and when we come back, I'm going to have you code the intersection for two lists, and then I'm going to have you code another intersection for multiple lists. So yeah, I'll start the timer for 5 minutes. I'll see you all back here in 5 minutes, and yeah, I'll see you shortly. Okay, so let's see. For this, for coding the intersection, let's just do 3 minutes on this. I think it'll be pretty quick, and if we need more time, we'll add that time in. So let me give you a little starter code. Right, intersection, and we'll just call this intersection. And you'll pass in 2 sets, set 1 and set 2, and code for the intersection of those. Okay, so let's do that. And go for it. Okay, so I'm going to start coding through this, and we just want to think of, you know, what is the most straightforward way that we can do this. So the first thing I'm going to do is I'm going to make a collector, this list accumulator, called, I'll just do set intersect, right? And this is just going to be an empty list. And then I can look at each item in set 1. If that item is in set 2, right? This is just how logically we can think about this. If that item is in set 2, then it belongs in the intersection. So we can say set intersect.append, and we can append the item. So it's just that, and let's return the set intersect. And let's call this on lists 1 and 2. Set 1 is not defined because it is not. It's actually list 1 and list 2. Chemistry and botany. So let's just verify that. Botany is shared, we can see. And chemistry is shared, we can see that too. But none of the rest of these are, so we didn't include them in our intersection of list 1 and list 2. So I'm going to have you code the intersection of multiple sets now. So actually, why don't I code this one? Because I want you to code set difference and get down to set complement as well. So when we're thinking about the intersection of multiple sets, we can go ahead and use that same star args approach. Right, so I'm just going to call this intersection multiple, and this is going to be star, and I'll call this multiple sets. I think that's what I called it above as well. Now, again, I can create this collector, right? Set intersect, and I want to do a little bit of qualification of what we're getting, right? So if the arguments are greater than 1, okay, we cannot have a lopsided intersection, right? We can't say A intersect nothing over here, right? We need to have at least 2 sets that we're passing in. If we're not passing in 2 sets, then we're assuming that A is intersecting with an empty set, like a null set. And obviously if you've got a set that has stuff in it and you try to intersect with something that has nothing in it, well, there's no intersection there, right? So we would expect to return this empty set as so. So I'm just going to put in a little bit of safety here, and I'm going to say if the length of our multiple sets argument is greater than 1. That might be what, a way that we start doing this. And I'm going to make this just a little safer, and I'm going to say if that first set that we pass in, arg sub 0, if the length of that is greater than 0. Okay, so now we know that we are performing a valid intersection, and we're not going to try to perform the intersection if either of these things is not true, right? We need to have some element in one of our sets, in our first set that we pass in, and we need to have some element in. We need to have at least one set. Now, if you're paying attention, this isn't completely safe because we're not checking that because what if the first set we pass in is empty, but the second one is not, and the third one is not? Well, in that case, we should still want to perform this operation. But I'm going to just do this simple safety mechanism with the assumption that we aren't going to pass in a null set on the first in the first set. Oh, cool. You're pointing out the thing that I just noticed. Awesome. Okay. So once we do that, we can just check every element that's in that first set, right? We don't need to traverse all the sets necessarily because if something doesn't exist in every set that we pass in, well, it doesn't really constitute an intersection. So let's go ahead and see. So for each item in args sub 0, we're going to check every one of those. And I'm just going to make a flag here. Is it a member? Is it part of the intersection? I'm going to default that to true, and then I'm going to say for each set in all the others. So this should not be args. I keep doing that because I am used to naming this args. I'm trying to name things slightly more meaningful, even if they are the args. So args is our multiple sets here. If the item is not in, right, this is a reference to the item up here. If the item in that first set that we're traversing, if it's not in any of these other sets, then we can change is member to false. And we can break, because we don't need to check anything further, right? If because this item does need to exist across all the other sets in order to constitute a member of the intersection. Okay, so then I can just check if is member is true, and if it is, then we can append to our set intersect that item. So there's a little more complexity in this one. I think it's not quite as straightforward, not quite as simple as the others. So for here we'll just return the set intersect. Okay. And let's try printing the intersection for multiple items. We'll pass in list 1, list 2, and list 3. We might get an empty list back. I don't know if I put anything that was shared across all of them, but let's find out. I didn't, or it doesn't look like I did. So let me modify this slightly. What's something that exists? Let's do botany. Let's just put botany into this third one, and now we should see something that we should see botany as the intersection of all three of those. And we do. Awesome. Okay. So the next thing we're going to look at, the next operation, is the difference of sets. And this one, when we were looking at the intersection and the union, it didn't really matter, right? It didn't really matter if we said, A intersect B or B intersect A. Those are actually equivalent, right? Same goes for A union B. This is the same as B union A. The result of those two operations is going to be different. Now, that's not going to be true for the difference. So the difference of A minus B is not equal to the difference of B minus A. And I'm just going to justify this with a quick picture. That's S, and then we've got A and B. The difference here is everything that is in A that is not in B, right? So if that's the case, then we are dealing with this. That would be A minus B. If we're considering B minus A, then that is the difference. That is everything that's in B that is not in A, and that would look like this. So you can see that these are two different concepts. A minus B is going to be different from B minus A. So I hope that explanation is pretty straightforward. Anything that, let's say you have A, anything that is in A and is also in B, if you're doing A minus B, or the difference between A and B, you should remove anything that exists in both from A. Okay? Likewise, if you have B minus A, you should remove anything that exists in both from B. So, with that in mind, you're going to code the difference function for two lists. And yeah, let's do 4 minutes on this. And then, yeah, let's do 4 minutes on this. I think that's a good amount of time. So I'm not going to give you any starter code on this. It's just, def difference list 1 or set 1, set 2, right? So it's the same type of starter code that we did before. And I will do 4 minutes on this and go for it. Okay, there's some good solutions in there for the set difference, and I'll go ahead and code something too. And just do a little bit of delineation here. So set difference, the difference of set 1 and set 2, And again, I'm just going to make this simple collector as a list. And I'm going to say for each item in set 1, if the item is not in set 2, then we can say set difference dot append that item. So pretty straightforward. And then, of course, return those. So if we're looking at the difference between, let's say, list 1 and list 2, we can compare that to the difference between list 2 and 1. So list 1 minus list 2, and then list 2 minus list 1. Okay. So let's kind of just look back at these. This is just everything that's in list 1 minus list 2 is just what does not exist in the intersection of the two, right? So we can think about the difference as being list 1, also list 1 minus the intersection of list 1 and list 2. So that's another way to think about this. Cool. Now that we have the difference, there is a very key operation to understand known as the complement. Oh, and I don't know if this is obvious, but we can't, like, the difference operation is only going to be between two sets. We're not going to, it is a sort of linear operation because the order of the events matters, right? List 1 occurring before list 2 is different from list 2 occurring before list 1. So we're not going to write a difference of multiple sets here. That wouldn't be sensible. So let's consider the complement. The complement is, we can think of the complement as being the difference between our sample space and a given event. So let's think about this. This is going to come up a lot in a lot of different areas. So the complement is going to be, let's say we've got S here, that's our sample space, and we have A in here. If we are thinking the complement of A, then it's everything that is in our sample space that is not in A. Okay? So there are a number of ways that we write this. The way I tend to write it is like this. I read that as not A. We might write it like this, not A. Tilde A is not A. A with this kind of C above is the complement of A. All of these things are valid. I'm probably going to, I'm going to use these three. I don't really like this one so much, just because I didn't learn it that way. So I have it's like a hiccup when I'm trying to recognize it. I tend to default to this. In our notes, I have it written this way. Either way, any of these are the complement. Now, to be able to take the complement of something, you need to know the sample space. And so with that in mind, we want to define the sample space. Now, we're going to need that. And so let me just define that really quick here. We've got our list 1, list 2, list 3, and maybe I'll just copy those again and bring those down here. Okay. All right. So let's say we've got list 1, list 2, and list 3, and then let's say that there's some extra stuff too, and the extra stuff is going to be, I don't know, radiology, and astrophysics. How about that? So our sample space sample, our sample space, is going to be all of the possible elements. It's going to contain all of the possible elements. And that's easy for us to compose, given... sure, I'll put these in the chat as well. Yeah, good call. The sample space is easy to compose given the functions that we have already. So we have the union of multiple sets, and I can just pass in list 1, list 2, list 3, and this extra stuff. And why don't I do that? And I'll paste this in to the chat. And we can just take a look at our sample space. So that's it right there. That's everything. Of course, there's no duplicates. And what we want to consider is, in terms of the complement, is everything that is not in, let's say, list 1. Okay? So I'm going to leave that to you to figure out. You're going to write a function called complement, and this is going to have 2 parameters, right? It's going to take the sample space, right? The sample space, and it's going to take a set for which you're trying to find the complement. And let's do, let's do 4 minutes on this. I think that's good. All right. Let me just check that question really quick. Okay, great. Go to it. Okay, so there are different ways you could do this, and one way is that you could cycle through the sample space and collect anything from the sample space that is not in set one into some kind of collector. Now that would work and that would be fine, but you've got a function that will make this a little easier, and we can depend on that. So that is just going to be the difference between the sample space and set one. So with this, you can see there's this direct relationship. The complement is just a special case of the difference. And let's print the complement of the sample space with list one and just see what that gets. And so it looks like, well, as you can see, anything that is in set one has been removed from this output. So we just get everything else, right? Psychology, bioengineering, robotics, computer science, radiology, and astrophysics. Okay, so this is a simple approach. Of course, you could iterate through the sample space and collect everything that is not in set one. You don't have to build that dependency with the other function. Okay. I'm sorry, my cat is meowing at the door, and he's just gonna keep meowing. Give me just 1 second. Okay, thanks for being patient. The thing is, I opened the door and he walked outside and immediately started meowing to come back in. And I left the door open, and I think it confused him. So hopefully that buys us some time. All right. So let's look at, now that we've got all these functions, we can use some of them. And maybe I'll solve this first one. Yeah, I think I'm going to solve this first one to kind of give you a sense of the types of problems we're going to be looking at soon. So, actually, let me grab a smaller version of this. And we probably won't get through all the breakouts. In fact, we might only get through a couple of them. But that's fine. We don't always expect... We've covered the things that we really need to cover, and everything from here is going to be kind of priming our next lecture. So I'll call this, I'll just do breakout, and then I'll put the description of it here. And if I have that there, I don't actually need that. So, this is not, sorry, I just rebuilt these slides today. This used to be part of another problem. So let's just answer this one really quick. Which of the following would not be considered a random experiment? And just brief explanation. Let's just do 1 minute on this. The selection of a numbered ball from a bucket of numbered balls, the amount of time needed to wait for a taxi cab, or randomly selecting a colored marble from an urn full of numbered balls. Yeah, C. And why is that? What is it about C that doesn't make sense as a random experiment? Yeah, that's the assumption. The assumption is that these are numbered balls. They're not colored marbles, and we don't have any information saying there are marbles in this urn. So in that sense, yeah, that's that doesn't make sense. Okay, so now let's get to something with a little bit more to do. Okay. And I'll go ahead and walk us through this one. And if we have time, we'll do one more after this, and I'll have y'all do that. Okay, so we're going to write out the sample space for a random experiment that is defined as sequentially completing these steps. So the first thing, we roll a 4-sided die. The second thing, we flip a coin. And the third thing, we flip a coin again. So let's think about that first. We're going to write out this sample space. Now, we could do this manually, and that would be fine. But this is where having a procedural language really comes in handy. We don't need to write this out by hand. We could, right? We could write 1 tails, tails, 1 tails, heads, 1 heads, tails, 1 heads, heads, 2 tails, tails, and so on. We could do that exhaustively. Instead, I'm just going to define this thing called outcomes, and I'm going to say for die roll in range, let's do 1 through 4. And I like using this 4 plus 1, right? That way we know we're really talking about a 4-sided object. And then we're going to flip a coin. And I'm going to call this flip 1. So for flip 1 in range, how do I want to do this? Let's do heads, tails. And then for flip 2 in heads, tails. And then at the end of all that, we can set our outcomes. So outcomes.append, and I'm going to just do this as a list. So this will be the die roll, flip 1, and flip 2. And so we should be able to see for outcome in outcomes, we should be able to see each outcome. So let's make sure that that works. Yeah, and it looks like it does. Okay. So notice 1 heads heads, 1 heads tails, 1 tails heads, 1 tails tails, 2 heads heads, 2 heads tails, and so on. As we progress forward, I'm going to be making a case for counting as an approach to understanding probability in a similar way to sort of as a intersecting approach to sets as a way of understanding probability. So let's consider the next part of this, which is list the sample points in the following events. So A is the event in which the die roll results in exactly 1 pip showing. Okay, well, you know, if we look at this, we can see that there should be 4 elements that meet that criteria. Now, if we want to do this in a procedural way, we can say A, right? A is our subset, or our event, right? So A, we can iterate through outcomes for outcome in outcomes. If that outcome sub 0 is 1, then A dot append that outcome. So we can go ahead and look at that and see what we get. So for outcome in A, let's go ahead and print that outcome now. So 1 heads heads, 1 heads tails, 1 tails heads, 1 tails tails. Those are the 4 outcomes that that fit into the event A. So let's look at B now. The event in which at least one of the coin flips results in heads. Okay. So I'm just going to copy all of this. We're going to use this same accumulator list collector approach. So for each outcome in outcomes, I'll just rename this B. If outcome And let's do this. If the outcome.count of heads is 1 or greater, so greater than or equal to 1, then b.append that outcome, right? So we can then see which outcomes in our sample space satisfy event B. And let's just scan through these. Oh, wait a minute. One of these is not correct. So, interesting. One heads heads, one heads tails, one tails heads, one tails tails. What am I doing wrong here? Is anybody seeing my error? Am I still printing A? Oh my gosh. Yes, I am. Thank you. It's like the most obvious thing. Yeah, there we go. That's better. So one heads heads, heads tails, tails heads, heads heads. We're not seeing anything in here that has 2 tails. And so we are satisfying that event B. And then the last part of this lists the sample points which are in the union of events A and B from above. Well, this is nice because we have a union function, right? So we have union, and we can just pass in A and B and see a result. And why don't I do this? Let's do for outcome in the union of A and B. Let's print that outcome. Okay. And, we could potentially consider, what outcomes we've excluded from this, right? So why don't I do that? Since we don't have enough time, we don't have quite enough time to look at another breakout. Why don't we just kind of build on this a little bit? And let's say so in the union of A and B, what elements are not present that are present in the sample space, right? So how could we do that? What would be a way that we could do that? In just a quick Python code snippet. Yeah, we could use the difference. Yeah, so we could just do this. We could just take the difference between what did we call it? We called it outcomes. Outcomes and the union of A and B. So we can just get the difference of that. We could get the complement. That would also work. But either way is fine because essentially the complement and the difference are going to give us the same result in this case. So it looks like 2 TT, so 2 tails tails, 3 tails tails, and 4 tails tails are the elements that have been excluded. Okay, so let's call it there for today. There are a few more breakouts in here, and the solutions are with the slides. So if you want to take a look at these, if you're finding any of this to be more challenging than you can understand while I'm kind of going through it, then definitely go back and look at these slides, these other breakouts. There's another problem here that's very much like the problem we just did. You can solve it in a Python procedural approach. Notice here I'm using a tilde to represent not, just so you know. So this would be the intersection of A and not C. And then this would be not the result of the intersection of A and C. Yeah, and there there's the solutions. You can solve these. Like I said, you can solve these either using Python or pen and paper. Cool. Yeah, so that's lecture for today. Stay on if you have any questions. I'm gonna go ahead and stop recording. And yeah, thanks so much. Feel free to sign off or stay on if anything is shaky or if you have any other kinds of questions.